Here's problem 912. A 3 kilogram mass is sliding on a horizontal frictionless surface with a speed of 3 meters per second when it collides with a 1 kilogram mass, initially at rest as shown in the figure. The two masses stick together and slide up a frictionless circular track of radius 0.4 meters. To what maximum height, h, above the horizontal surface will the masses slide? Alright, so what we really have here are two problems in one. We're going to have a collision between these two masses, and that will involve conservation of momentum. And then we'll have a second problem, which will involve the second mass, or the masses, sliding up the incline, or the curved incline, to some height, and that will be conservation of energy. So we're going to have these two problems to deal with. Let's look at the first problem first. We have conservation of momentum, so we're going to have mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, equals mass 1, velocity 1 final, plus mass 2, velocity 2 final. The one equation to rule them all for all these collisions. We want to use this formula, and we know that mass 1 is 3 kilograms. Velocity 1 initial is 3 meters per second. Mass 2 is 1 kilogram. Initially it's at rest, so velocity 2 initial is 0. And we're going to see that these masses stick together, so really we're going to have mass 1 plus mass 2 with one common final velocity. V1 final and V2 final will be the same. So we have 3 times 3, 9, is equal to mass 1, 3, plus mass 2, which is 1, times V final. Or V final is going to be 9 divided by 4, which would be 2.25 meters per second. Nice to know. I've always wanted to know that. But we want to find how far these two masses stuck together will go. Well, this next problem then is a matter of conservation of energy. We're going to go from point A to point B, and energy will be conserved. So we would write down the one equation to rule them all, which is that the kinetic energy at A plus potential energy at A plus any work done along the way will equal the kinetic energy at B plus the potential energy at B. Next question is to which if any of these terms might actually be 0. Well, the curved tract is frictionless, so there's going to be no work done along the way. We're going to go as high as we can go and go no further, so we're actually going to stop momentarily at this greatest height. So our kinetic energy at point B is going to be 0. And we can define our level at point A, the lowest level, as being 0, so our potential energy at A is going to be 0. So now we're left with that the kinetic energy at A, 1/2 mass, actually the total mass, m1 plus m2, times the velocity at point A squared, equals the potential energy, mass 1 plus mass 2, times g times h. We can cancel out the mass on both sides and solve this for h. So we'll have h is equal to 1/2 the velocity squared divided by g, or velocity squared divided by 2g. Our final velocity was 2.25 meters per second, so we'll square that over 2 times 9.8, and this will give us 2.25 squared, 0.258 meters. So the final position, final height of these two masses stuck together is 0.258 meters, or 25.8 centimeters. The fact that the tract is curved is not going to matter. We're just going to go, even if it curves back this way, we're just going to go to this height, and that is our pure height above the ground.